timing violations don't happen because your system is slow. They happen because time was assumed, not engineered. Think about it. A digital system is built on a single, crucial promise. Data will arrive before the clock asks for it, and it will stay stable long enough after the clock samples it. This is the heartbeat of logic. But when that promise is broken, your system doesn't crash loudly. It fails silently, corrupting data in ways that are maddening to debug. So what breaks this fundamental promise? The first and most common culprit is path delay. Every logic gate, every wire on a chip, adds a tiny delay. It all adds up. You might have a perfectly logical design, but if the signal has to travel through too many gates or across a long, winding path, the data simply arrives late. It misses its appointment with the clock. Imagine a runner trying to cross the finish line before the timer buzzes. If the track is too long, they won't make it. The second cause is clock uncertainty. You might think the clock signal reaches every single part of your chip at the exact same instant. It doesn't. This difference in arrival time is called clock skew, and it effectively shifts the finish line for different parts of your circuit. Then there's jitter, where the clock edge itself isn't perfectly stable. It wobbles back and forth with every cycle. So even if your logic is incredibly fast, a treacherous clock can still betray you. It's like the finish line is constantly moving. Third, the delicate balance between setup and hold time. To fix a setup violation where data arrives too late, you might speed up the logic path. By making that path faster, you might cause the data to change too quickly for another part of the circuit, creating a hold violation. It's a classic case of whack-a-mole. Fixing timing isn't about solving one problem. It's about maintaining a fragile equilibrium across millions of paths. It's a system-wide balancing act. Then, we have the real-world variables, voltage and temperature. When your device's battery runs low, the lower voltage slows down the transistors. When it heats up, the physical properties of the silicon change, altering signal delays. The conditions changed, and the timing promises were broken. And finally, the most dangerous cause, false assumptions. Engineers rely on average delays instead of accounting for the extremes. They treat timing closure as just another checkbox to tick on a project plan. But timing isn't a feature you add at the end. It's the foundation. Timing violations aren't just bugs. They are consequences. They are the inevitable result of not respecting the physics of time in a digital world. If you don't design for time, time will break your design. Stay sharp.